Select relationships between distributions. In this section, we will discuss some relationships between some of the distributions we've covered, and explore a couple of new distributions. Recall the geometric distribution. A geometric random variable counts the number of failures before the first success in a series of trials. The exponential distribution is analogous to this, but we are now waiting for a success in continuous time, where successes arrive at a rate of lambda successes per unit of time. A continuous random variable y is said to have an exponential distribution with parameter lambda if its probability distribution function is f of y equals lambda times e to the negative lambda y, where y is greater than 0. Furthermore, y represents the waiting time until the first arrival of a success. Let's look at an example. The time it takes for a network server to respond to an incoming request follows an exponential distribution with an average of lambda equals 3 server responses per minute. A. We want to find the cumulative distribution function f of y. Okay, so we're going to find capital F of y, which we know is equal to the probability that our random variable y is less than or equal to some value little y. And this is the integral from 0 to y of our PDF, which is lambda times e to the negative lambda y, dy. Now we know that we've got a lambda out here, so we're just going to go ahead and bring that out. And when we take the integral of e to the negative lambda y, we get negative 1 over lambda times e to the negative lambda y. And we cancel out these lambdas, and it looks like we're left with negative e to the negative lambda y. And we need to evaluate this from y down to 0. So when we plug the y in, it looks like what we're going to get is just negative e to the negative lambda y. And we subtract. Now we're going to plug 0 in, and it looks like when we plug 0 in place of y, we're just left with negative 1. So simplifying a little bit, we get 1 minus e to the negative lambda y, and that's our cumulative distribution function. Now here, since lambda equals 3, that will give us 1 minus e to the negative 3y. B. What is the probability that it will take less than 40 seconds for the server to respond to a request? Well, let's first note that our PDF was given in minutes, and here we want to find the probability that y is less than 40 seconds. So we're first going to take this and rewrite this as the probability that y is less than 2/3 of a minute. Well, now note that this probability is just equal to capital F of 2/3. And this equals 1 minus e to the negative 3 times 2/3. Now we can simplify this to 1 minus e to the negative 2. And this is approximately equal to 0.8647. If y follows an exponential distribution with parameter lambda, the mean and standard deviation are both given by 1 over lambda. So in the last example, if there are an average of lambda equals 3 responses per minute, then the average response time is 1 over 3 minutes, or 20 seconds. The moment generating function is given by m sub y of t equals lambda over lambda minus t, and here t is less than lambda. One key feature of exponential distributions is a special property called the memoryless property. This states that even if you've waited for hours or even days without success, the success isn't any more likely to arrive soon. Suppose that you've already waited s minutes for a success. The probability of waiting another t minutes, for a total of s plus t minutes, is exactly the same as the probability of waiting t minutes. Now let's take a look at this. It's easy enough to show that the probability that y is greater than or equal to c for some value c equals the integral from c to infinity of lambda times e to the negative lambda y dy, which equals e to the negative lambda c. So the conditional probability that y is greater than or equal to s plus t, given that y is greater than or equal to s, is equal to e to the negative lambda times s plus t over e to the negative lambda s. This simplifies to e to the negative lambda t, which is equal to the probability that y is greater than or equal to t. So we see that waiting s minutes doesn't really have any effect on whether we need to wait t more minutes. Now think about the memoryless property implications for a moment. Sometimes, particularly in the world of gambling, people may feel like it's their time to win, simply based on the fact that they've waited long enough. However, if the distribution of time before a win is exponential, as it often is, then that's a faulty way of thinking, because it doesn't matter how long you've waited before the first success. And clearly there are other phenomena that do not follow exponential distributions, based purely on the fact that the memoryless property doesn't apply. For example, the breakdown time for machines depends on how long they've been running, and the same could be said for human lifetimes. So we've seen that the exponential distribution is the continuous equivalent of the geometric distribution. But exponential distributions are also closely related to Poisson distributions. Recall that a Poisson distribution with parameter lambda provides a way of modeling the distribution of the number of y rare events that occur in space, time, or volume, where lambda is the average value of y. Let's suppose that phone notifications arrive according to a Poisson process at the rate of lambda per hour. That is, y has a Poisson distribution with parameter lambda. Now we know that we could find probabilities about how many notifications arrive over a certain period of time. Suppose, though, that we are asked this question: how long is it before the first phone notification arrives? How about the time between the first and second notifications? Note that the first question is just asking about the waiting time before the first success, which has an exponential distribution with rate lambda. The second question is a little more complicated. It's asking about how long it takes before a notification arrives once the first one has arrived. Now one might think that this time depends on how long it took for the first notification to arrive, but that's not the case because of the memoryless property. No matter how long it took for the first to arrive, the time it takes for the second to arrive will also have an exponential distribution. Similarly, the waiting time between any two notifications will be exponential with rate lambda. Let's look at an example. An online shopping platform aims to enhance its website reliability. The IT department has observed that downtimes follow a Poisson process with an average rate of lambda equals 2.7 downtimes every month, which we define as 30 days. We want to find the probability that the website is down at least once during the month. Okay, so first of all, we notice here that we're being asked about the number of successes that occur over a given period of time, which we know means that we have a Poisson distribution, and here our lambda is equal to 2.7. And so now we're going to try to find the probability of at least one success over the month, and that is equal to 1 minus the probability of no successes, which is equal to 1 minus e to the negative 2.7 times 2.7 to the 0 over 0 factorial. We're just plugging this into the Poisson PDF. That gives us 1 minus e to the negative 2.7, which we find to be approximately equal to 0.9328. Now we could also find this probability in Excel using the Poisson dist command. Now we want to determine the probability that the website operates without downtime for at least half of a month. Okay, so let's define x to be the time before the first success, or downtime. Then we know that x is exponential with lambda equals 2.7. Now what we're interested in is that there is no downtime for at least half a month. In other words, we want x to be greater than or equal to 1/2. And we want the probability of this event. Now the probability that x is greater than or equal to 1/2 is equal to 1 minus the probability that x is less than 1/2. which is equal to 1 minus capital F of 1/2. And remember, F here is the cumulative distribution function. And when we have an exponential distribution, we know that capital F of x is equal to 1 minus e to the negative lambda times x. So the probability that x is greater than or equal to 1/2 is equal to 1 minus e to the negative 2.7 times 1/2. And we find this to be approximately 0.2592. Now we want to find the probability that the website operates without downtime for at least half of a month, given that it has already been running smoothly for the first third of the month. And so I'm going to write this down as the probability that x is greater than or equal to 1/2 with the condition that x is greater than or equal to 1/3. Now let's go ahead and write this as the probability. I'm going to write down the conditional part first. X is greater than or equal to 1/3. And I want to write down this first part here involving 1/3. So I have x is greater than or equal to 1/3 plus 1/6. And we can see here that 1/3 plus 1/6 gives us 1/2. But now note that this is in the form x is greater than or equal to s plus t, given that x is greater than or equal to s. And we know by the memory list property that this conditional probability is just equal to the probability that x is greater than or equal to t. And so the probability that x is greater than or equal to 1/2, given that x is greater than or equal to 1/3, is the same as the probability as x is greater than or equal to 1/6, the difference between 1/2 and 1/3. Well, now this just equals 1 minus capital F of 1/6, which is equal to 1 minus e to the negative 2.7 times 1/6. And we find this is approximately equal to 0.6376. Okay, so we've seen that an exponential random variable represents the waiting time for the first success to occur, or the waiting time between any two successes. Suppose, however, that we were interested in the total waiting time for a given number of successes to occur. Let's let y represent the total waiting time for n successes to occur in a Poisson process with the parameter lambda. We will call the waiting times between successes y1, y2, y3, all the way up to yn. Now it should be clear that y1 has an exponential distribution with parameter lambda, since this is just the time before the first success. The time before the second success is y1 plus y2. And extrapolating, we find that the time before the nth success is y1 plus y2 all the way up to yn. Now here, each y sub I is exponential with parameter lambda. So the question is, what's the distribution of y which equals the sum of all of the y sub i's? It's a new distribution we call the gamma distribution. The gamma distribution has two parameters, alpha and beta, and it has a density function given by f of y equals 1 over gamma of alpha times beta raised to the alpha times y raised to the alpha minus 1 times e to the negative beta y. Here, alpha, beta, and y are all greater than 0. The quantity gamma of alpha is known as the gamma function, and it can be shown that gamma of 1 is equal to 1, and that if n is a positive integer, then gamma of n is equal to n minus 1 factorial. Otherwise, it's defined as gamma of alpha equals the integral from 0 to infinity of y to the alpha minus 1 times e to the negative y. In the case of the total waiting time before the nth success, we find that y has a gamma distribution with parameters alpha equals n and beta equals lambda. Let's look at an example. Accidents occur at a particular intersection according to a Poisson process at a frequency of lambda equals 16 accidents per year. What is the probability that the third accident will occur within the first month? Okay, so I'm going to let y be the waiting time for the third accident. And we can see here that n equals 3, and we were told that lambda equals 16. And so we know that y, the waiting time for the third accident, has a gamma distribution, where alpha, which equals n, is 3, and beta, which equals lambda, is 16. So let's go ahead and write down the PDF. We have f of y equals 1 over gamma of 3 times 16 to the third times y squared times e to the negative 16y. Now remember here that gamma of 3 is just 3 minus 1, which is 2 factorial. So we have 1 over 2 factorial times 16 to the third, which gives us 2048. And we have y squared and also e to the negative 16y. Well, now we want to find the probability that the accident occurred in the first month. So we want y to be less than or equal to the first month. But remember here that lambda is given to us in terms of years. There are 16 accidents per year. So let's rewrite this as the probability that y is less than or equal to 1 over 12. Well, now this is equal to the integral from 0 to 1 over 12 of our PDF, which is 2048 y squared times e to the negative 16y dy. We can do this integral. It's a little bit complicated. We'd have to use integration by parts. And if we take that approach, then what we get here is e to the negative 16y minus 16y times e to the negative 16y minus 128 times y squared e to the negative 16y. And we need to evaluate this from 1/12 down to 0. And when we throw this into the calculator, we find this is approximately equal to 0.1506. So we see that these types of integrals are certainly doable, if complicated, but we often use technology to find these kind of probabilities. Here in Excel we have the gamma.dist command. One thing to be aware of, though, is that Excel uses a slightly different version of the gamma distribution. The primary difference is that instead of using the value for beta, we have to put in the reciprocal. So in this case, instead of putting in 16, we put in 1 over 16. If you are familiar with the statistical programming language R, then we can also find this probability using the pgamma command. We've introduced the gamma distribution as a model for the total waiting time for a given number of events to occur, but it's also used for other type of probability processes. The shape of the distribution depends on the parameters alpha and beta. Let's observe the effect of changing alpha and beta on the shape. In general, the gamma distribution is skewed to the right, which makes it a good model for certain phenomena. If we have a gamma distribution with parameters alpha and beta, then the mean is given by alpha over beta, and the standard deviation is the square root of alpha over beta. One thing to note here before we move on to an example is that since we've been exploring connections between different distributions, if alpha gets larger and larger, then the gamma distribution approaches a normal distribution. Let's look at an example. A rehabilitation center finds that recovery times for a certain type of sports injury can vary depending on the patient's age, physical condition, and adherence to the program. The recovery times in months are modeled by a gamma random variable, where alpha equals 4.5 and beta equals 0.5. We want to know what is the average recovery time. Well, we know that the mean of a gamma random variable is mu equals alpha over beta. So the average recovery time is mu equals 4.5 over 0.5, 5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0 What proportion of patients have recovery times greater than 6 months? Well, I'm going to use technology here to do this. In Excel, I can use the gamma.dist command. Now, I'm subtracting from 1 here because I'm finding a right tail probability. And remember, Excel uses a version of the gamma distribution where we have to enter 1 over beta instead of just beta. We find the proportion of patients who have recovery times greater than 6 months to be 0.7399. And I'll note here that we could also have used the pgamma command in R to find this. Would it be unusual for a patient to have a recovery time less than 4 months? Again, we'll use the gamma.dist command in Excel. We find the probability to be 0.088587, which is somewhat small, but likely not quite to the point to where we would call it unusual. And again, we could have found this probability in R. As we wrap up looking at some of the connections between various probability distributions, I hope it's clear that understanding these relationships enhances our ability to model and interpret a wide range of real-world phenomena.